right, so hello everyone. Tonight I'll be talking about implementing live by leveraging Rust in WebAssembly. It probably won't be as cool as last month's talk about the CO2 measuring device by tanks. That was pretty cool, but hopefully it'll be cool enough. So let's dive right in. So really quickly, my name is Antonio. I do happen to have a very long last name in the Spanish tradition of last names. I moved to Berlin a couple of months ago. I'm now working as a full-stack engineer at Lipsum. We're actually just like a couple of blocks from here, so it's a pretty short walk to come here. And we're doing a lot of good stuff at Lipsum, but we're not doing any Rust yet. So I'm here mostly as a hobbyist. I've started learning Rust this year. I'm mostly interested in WebAssembly as a web developer myself. And to give you kind of an idea of how good I am at Rust right now, so this is my third meetup. And in the two previous quiz, I was able to score 0 points in both of them. So I hope I can make it 3 out of 3 this time. But yeah, so just like, I may actually be the one asking you questions at the end of the talk. All right, so basically what I'm going to be talking about is the official Rust WASM tutorial. I'm not going to be going too much into details. I just want to give kind of an overview of the state of the art of Rust and WASM currently. So just kind of looking at the tools and seeing like how like things fit together. If you're interested, like definitely do look it up. It's pretty nice. And for those of you who are not familiar with the game of life, really like the TLDR is that it's a 0-player simulation game where you have a universe that evolves with time, and where like cells are dead or alive, and then the universe like evolves by like calculating the next set of the cells based on the previous set of the cells. So pretty simple set of rules here. So it looks like this. I don't know why it's like so laggy on this GIF, but hopefully it won't be that laggy on the actual game of life. And so the rules are pretty basic. There's like only like 4 rules to the game. So here, a dead cell is white, a live cell is gray. So if a cell is alive and it has less than 2 neighbors that are alive, that cell dies in the next generation. If it has 2 or 3 cells are alive, that cell stays alive. If there's more than 3 cells, that cell dies. And if that cell is dead and there's like exactly 3 neighbors that are alive, that cell becomes alive. In every other case, the cell keeps the same state. Okay, so what is WebAssembly? Why should we care about WebAssembly in the first place? So here's the Wikipedia definition of WebAssembly. So it's a binary instruction format for stack-based VM. It's quite interesting to see that there's nothing really web-specific about WebAssembly. For now, like it's only shipped in major web browsers, but in the future, like we can think of having that VM in other places as well. So it's designed to be like a target for high-level languages like C, C++, and Rust. As a JavaScript engineer myself, like it's kind of fun when I see the word high-level and C, C++ in the same sentence, but sure. And what's quite impressive as well is that it was first announced like 4 years ago, but now all major browsers support it. So unless you still work with IE in some way or another, you can ship WebAssembly to production. And there's actually a few companies who are like already like shipping out WebAssembly to production. And so why Rust? So I took this screen from the official Rust WebAssembly website. But as a web developer, like I've said, like the three main reasons why Rust and WebAssembly makes sense to me is that first of all, it's a memory-safe language. I don't trust myself to write memory-safe language in like C or C++. Second of all, the zero-cost abstraction is pretty cool. Like you have very nice ergonomics to the language. And then I think like third of all is the community. So it's basically all of you here. It's a very friendly and welcoming community that we have in Rust. And it's quite impressive to see how Rust is able to federate such a diverse crowd. Like you have people like coming from like web, doing WebAssembly. You have people doing like embedded programming, people doing like system programming. You have like blockchain stuff as well for some reason. So that's pretty cool. Okay, so enough talking. Let's kind of dive into some code. This is when like everything breaks usually. So, oh yeah. So welcome to VS Code. So basically, here we have a basic setup for Rust and WebAssembly. So what I'm mostly using here is going to be a WASM pack, which is a wrapper around Webpack, which allows to do a bunch of stuff. But what we're going to be using it for is basically just to build Rust into WebAssembly. And then we have like a dev server here running, which will just like serve whichever we like feeding into it to a browser. Okay, so if you basically just take the sample code from the tutorial, like this is what you get pretty much in Rust, just like a simple public greet function that's going to be like surfaced into a WebAssembly. WebAssembly WASM pack then like compiles it and like creates kind of this wrapper in JavaScript that allows us to like import it into our JavaScript code, and then it does also give us a nice WebAssembly file. So it's a binary file, like this is the text format of WebAssembly. It uses S expressions, so that's pretty cool. Looks like Lisp. But we're not going to be like looking too much into this. And so what we're going to do here in our index.js is that we're going to import WASM from WASM Game of Life. So this is just like doing like any importing JavaScript nowadays, and then we're just going to call like the greet function with Game of Life, which would then alert hello Game of Life, hopefully. So if here, yay, hello Game of Life. Thank you. That's all for tonight, goodbye. Okay, cool. So let's actually like start like looking at the implementation. So I'm gonna do a pretty nice mix of live coding and time traveling. It's called Git tags. So I'm gonna be like checking out tags along the way. So let's start with this one. We're gonna build this. So basically what I've done here is that I just implemented the Game of Life using Rust. So I don't want to like go too much into details into this. It's just like pretty straightforward Rust. So Rust, you have like an enum for the cell that can be the dead or alive. Then you have a struct for the universe with the height, and then a vector of cells. Then there's a few functions, there's a few methods on the universe to count the number of live neighbors and to get the index. So this is useful because we are storing the universe in linear memory. So it's just like a one-dimensional array, and we have like a two-dimensional universe. So basically what we're doing is that we're storing everything together. And the get index will just like flatten that out for us. So we pass a row and a column, and then it gets us like row times width plus column to get the actual index in memory. And then we're like going to surface a few methods to WebAssembly. So a tick method to generate the next generation of the universe, which we can see here with like the rules that I explained previously here. A new function to create a new universe. And in this case, we're going to have a render function, which will generate a string out of that universe. And what we're going to do in the JavaScript side, we're going to have like a loop that would like run on every like animation frame. We're going to call the tick function of the universe, and then we're going to like plug in all of the string that comes out of the universe into a pre-HTML tag. Sounds pretty inefficient. It is pretty inefficient, but let's have a look anyway. Yay! So now we have cells here. Cool. So yeah, you might be thinking like there's probably like better ways to communicate between WebAssembly and JavaScript than like just passing strings around, and you're probably right here. The good thing is that JavaScript has access to the same exact memory as WebAssembly. So we can, from JavaScript, read all of those cells directly instead of relying on the universe passing out a string or not. So let's, again, do the magic of Git tags to implement that. So here on the universe, we haven't changed much. The main change that we have are those like three getters, sorry. So we can get the width, the height, and then a pointer to the cells vector from Rust. And then on the JavaScript, we also like change a bit the implementation here. We're now using a canvas instead of a pre-HTML tag. So I mean, this is just like very canvas DOM kind of API thing. So this just draws the grid, and then this would just draw the cells. The important thing here is that we're getting the cells pointer from the universe, and then we're like creating array buffer here that would then point to that same sales pointer and then read every single cell here for the whole universe. Then you just loop through it, and then you just like draw all the cells here. So if we look at the result now, okay, we need to probably compile WebAssembly first. Up. Okay, so that's what we get now. A universe 64 by 64 with like cells moving around, dying and living, a few gliders here and there. Yeah. So as you can notice as well, like the universe is infinite. So that means that like whenever it goes to the border, like it wraps around the universe. Okay, cool. So I guess so far so good. The most important, interesting part here. Oh, I guess I can quickly show something else. We can also like add interactivity, meaning that we can not only read from that memory, but also kind of like talk back to WebAssembly. So here, what I've added is a pause button, and you can now actually draw on the canvas as well. So I can make a nice glider here. Yay. Okay, cool. So I guess you can do a lot of things in WebAssembly. Does it make sense to rewrite everything in WebAssembly? Probably not. And if you actually are looking into WebAssembly, it's probably because of some like heavily computational stuff that you want to be more performant with. So let's have a look now at how we can measure performance and see if this is the most efficient way of doing it and how we can improve on this implementation, because it's not so efficient as it is now. Okay, so what we're gonna do very quick is that we're just gonna add like an FPS counter. So again, this is just like JavaScript. We measure the number of frames per second and we just like display it on the counter. So if you come here, we can see that, okay, like we're like at around like 60 frames per second, which is quite nice. Okay, let's see what happens if, for example, we double the size of the universe. If I can find the code, oh, yeah, here. Okay, let's double the size, rebuild. And now, okay, it's still not too bad, but we're like at 40 frames per second. So it's quite a dip here. So let's see like what happened here. I guess the intuition is probably that like somewhere like in the Rust implementation, we're like doing some things that are not so efficient. But it's always good to look at actual numbers to drive performance. So let's check out the next part. So to do that, what we're gonna do is we're gonna add like a timer. So here we're gonna create a new timer here, a new struct, which just calls console.time basically. And we're gonna time a very specific part of the code. We're gonna time the tick, because our intuition like probably tells us that like the tick is the slow part of our implementation here. Okay, so let's build this thing and then start our performance debugging. And also let me also grow the universe again. Okay, so let's open the browser here. Let's run performance recording. And so what we're gonna be looking at here is request animation frame. So like every one of those things, of those yellow things, is one update on the universe basically. And so if you look into here, we see that here's our universe tick. So here's our timer. We see that it's actually quite negligible compared to like the whole time that we're spending re-rendering the universe. So let's dig it up a bit. So if you open the GS flame chart, you can see that most of the time is actually spent in the draw cells function, and in particular in the fill style setter on the canvas. We can again like have a look here and see that actually like we're spending 57% of our time in the fill style setter on the canvas. So surprise, surprise, it's not Rust the problem, it's JavaScript. Okay, so let's look actually at the implementation and see where is that fill style here.
One quick question
Yeah.
while you're there.
Yeah.
Is it possible to also like look into the details of the WASM execution with like some source map or something? Or is that sort of a blob and you only see like?
You can actually use some of your the native tools to look at the performance of WASM. I'm not going to be showing it now because I haven't figured out how to do it yet, but like it's definitely possible. And yeah, there's not really like a source map for WASM. So whenever like you build WASM, you end up with like two types of files, either like .wasm files, which are binary files, and then .wat files, which are text-based files, which is what I kind of showed previously. But yeah. Cool, thanks. Oh yeah, so like this is literally like where we're spending 57% of our time. Like in the whole like application, like this is the place where like we're really like getting like stuck. And good thing is that there's quite an easy solution to this. So basically, instead of assigning a color on every single cell iteration, I think he agrees with me that like he doesn't like JavaScript either. Yeah, so instead of doing that like on every single like cell iteration, what we can do is move this outside of the loop. And so that's what we're going to be doing right away. Let's clean things up. And yeah, I mean, the only change we've done here is that we moved the style, field style outside of the loops. So we like setting it to like a live color first, then we like looping over the whole universe and only setting the live cells. And then we're doing the same thing with the dead cells here. So let's see if this actually solved our issue. Let's rebuild this, come back here. So if I do again, like yeah, we're back at like around 60 frames per second. Cool. Okay, let's try to like stress this a bit more. Instead of doing like one tick per render loop, let's try to do a lot more than that. Let's see. Let's try to do 9 ticks per loop and see what happens next. So it goes a lot faster. And we are back again to like 45 frames per second. And so in this case, I think like the intuition that like something in the universe tick implementation is probably like a bottleneck is probably a good intuition. So let's add a few more timers around. So like this is the timer we had previously for the universe tick, but now we're adding a timer for the allocation of new cells, a timer for the generation of the next cell, and then a timer for the allocation of cells. I guess like if you're a seasoned Rust developer, this is a bit of a smell. So you're like, okay, like maybe like we can do it in the better way without using clone here. But let's see like where is the actual bottleneck here. So let me build again. Up. Then we're going to use the same performance recording tool here. Up. A few generations. So let's look. So you can see that now, like in a single frame, we have like a bunch of ticks because we're like doing like the for loop here. And if you look closer, let's zoom in closer a bit. Okay, so you can see that surprisingly, allocating new cells and freeing new old cells is actually not that expensive still. And that most of the time is spent in the new generation implementation. And to answer your question, that's actually where you would be using like native tools to kind of try to see exactly what's happening at the WASM level and see like where the bottleneck is. I'll do a TLDR here. So the bottleneck is actually in our implementation of the live cell counter. In particular, using the modulo operator here is actually very expensive when we're like wrapping around the edges of the universe. Again, luckily for us, there's actually a very, very simple solution. So instead of using like the modulo, what we can do is just like use a wall of ifs and just like take every single like possibility into account. Like if you're like on the top row, like we look at the bottom row. If you're at the bottom row, we look at the top row, and the same on the sides as well. And this pretty much fixes it. So if you go back here, okay. Go back here, we can see that we are okay, kind of around 60 frames per second again. And some of the tooling around like Rust allows us as well to like run benchmarks. So I'm not gonna show that now, but I did run benchmarks at home before and after here. And what we can do is we can just use bench compare, and then we just compare before and after. And we can see here that like the new implementation is 8 times faster than the old implementation. Okay, so that's pretty much what I have. I also want to like kind of give a shout out to the tooling around WASM and Rust. I don't know how mature it is considered in the Rust community, but again, as a JavaScript developer, it takes me like 1 week to choose a front-end framework and configure Webpack. So anything less than that is very mature for me. So yeah, definitely, if you're like interested in this, definitely have a look at the official tutorial. It's pretty it goes like into more details to what I presented here. So yeah, that's what I have. Hopefully, you've learned at least one thing out of this, maybe. So yeah, thank you very much. If you want to dive more into this, like here are a few links that you can check. And I'm open for questions.
Questions?
Not too hard, please. Okay, go ahead. Yeah.
Have you used Rust-only web frameworks yet? Like I think there's one?
I haven't. I mean, I've mostly been playing around with Rust on my weekends and stuff, so I haven't really like looked at it in a professional way. I know there's like Rocket, which is a web framework for Rust, I think, if that's like similar to what you're talking about. But yeah, I haven't really done any of that.
Yes. How hard would it be, or if you have a React application and you would plug like the WASM pack into like the store, so like it can update like the store and all like the rendering is done from React? And have you thought about this at your company, like some parts of the code which use more computation, like does it make sense?
So surprisingly, we're not using React at the company, but like any, yeah.
What are you using?
We're kind of, it's a pretty old school code base, so we use still on AngularJS, but moving into Vue, yeah. That's what we're like planning to do. I don't think that like WASM makes sense in most cases. I think like it does make sense when you have like a very like heavily computational part of the application running on the browser, which for like most applications is not really the case. I think the best example I can give here is Figma, which is a collaborative design tool. So I know it's not the crowd here to talk about design tools, but what they've done like a couple of years ago is basically ship WASM, and so they have like the whole like design tool like on the browser, and it's super efficient and it's pretty well done. So I guess like from my perspective, like this is something I may not use every day at work, but like it's a nice tool to have in my tool set. Like if at some point like we reach any performance issues, I can be like, okay, like this part can be written in WASM, and then easily plugged into whichever needs to be plugged into it. To jump on the React part of your question, it's quite interesting because someone took the time to kind of rewrite the virtual DOM using WASM, and it's surprisingly not so much faster. Like it is definitely faster, but not at the point where it makes sense to rewrite everything in WebAssembly. Yeah. Any more questions? All good? All convinced that WASM is the future? Okay. Cool. Thank you very much.
You used the state order. Did you use Rust up for toolchain installation, or did you use anything else?
Yeah, Rust up. Yeah.
Okay.
I mean,
I'm not aware of any other method to install the WebAssembly compiler backend to install. Yeah. Other than Rust.
Yeah, it's all based on the same like Rust toolchain. Yeah. Yes.
One quick question: what were the pain points?
What were the pain points? It was surprisingly very easy, though, to be honest. I mean, except for the fact that I'm not like a well-versed like Rust programmer, so like sometimes like looking at syntax and like seeing like how things are plugged together. But again, like the tooling, I was able to like get everything installed in like 5 minutes. It works out of the box. I haven't had to like really like debug anything. The tutorial is pretty nicely like set as well, so just following the tutorial was like very easy. So yeah, I mean, happily surprised again as a JavaScript developer that like sorry, I won't say JavaScript anymore. I think like that's like like the but yeah, happily surprised that it was actually very painless. Yeah. Yes.
So you mentioned that there was something slow when setting the field something?
Yeah.
In the JavaScript code, and that's not possible to move that in Rust to make it faster in WebAssembly?
Would it make sense to move that to Rust? That's a good question. I think like there's a pretty big effort to like rewrite most of the dumb APIs using Rust and like shipping that in WebAssembly. I'm not sure yet if the benchmarks are really like favorable to that, in the sense that does it make sense to rewrite like a bunch of code like to Rust if it's still like allowing you to have like 60 frames per second. And I think the point here is that you don't have to rush to like the most performant solution, as long as the current solution like works for your use case. I think it's good enough, but I mean, it's definitely something that is possible, I think, yeah.
So you would be able to access the context API from the canvas in Rust, right?
I mean, it's just like a dumb API, so if you rewrite it with WebAssembly, you should be able to access it as well, yeah.